so just doing a quick go through the storage parts of the GCSE, and so we start with units, and it's not shown here, but 8 bits is like a bit is just one binary digit, so either a 0 or 1, and 8 of those make a byte. And then everything else is typically like built on bytes. So we have sort of going up in like multiplying by 1,000, we have 1,000 bytes is a kilobyte, then go up by 1,000 kilobytes is 1 megabyte, and then go up by 1,000 megabytes is 1 gigabyte, 1,000 gigabytes is 1 terabyte, and 1,000 terabytes is 1 petabyte, which is only really used if you're like thinking about like servers and stuff and more commercial things. Like, we're thinking on the scale of your personal computer, that's unlikely to have a petabyte. So anyway, so there are two sort of like main types of storage we have, which are primary and secondary memory on the computer, or primary and secondary storage. Anyway, primary storage stores data and programs that need to be accessed quickly, and there are two main types of this. One is RAM, random access memory, and it's called random access memory because you can sort of access any part of it as quickly as you can any other. Yeah. And so RAM, well, we use this for like the main memory of the PC, of your computer. And this stores the operating system, or the parts of the operating system that are currently loaded, programs and data that are currently in use. RAM is volatile, and that means that when it doesn't have power, it loses all the data in it. And it can be written to and read from. And the other type of primary memory is read-only memory. Now, read-only memory tends to be like a small amount of memory you have in your computer, and this is used for like when the computer first starts up, it reads this and it contains like a small program and data needed to start your computer up and sort of point it towards like the main operating system and things like that. And this is non-volatile, so even if it loses power, it still like stays the same, like that you don't lose the data. And this can only be read. That is why it's called read-only memory. And so secondary storage is used for longer-term storage of data and programs. Now, the thing is with these first two kinds of storage is like primary memory is they tend to be fast but also expensive. So we can't really use them for long-term storage because it'd be very expensive and inefficient. And obviously you're not going to be using all your programs all at once. Obviously, like, we want somewhere we can store things for longer, because if like you turned off your computer and all your programs were gone and all your like data was gone, that would be pretty bad. And so this is typically slower but much cheaper per like unit of storage than primary storage. And sort of the main types we have of it are magnetic storage. So this is like a hard disk drive. So this is like your traditional like large like spinning disk thing. So it has like a sort of metal disc in there that has the surface of this metal disc, like the magnetic field on it varies. So this is magnetized metal disc, and the data is stored on it by the magnetic field on it being varied, essentially. And typically these come at a like storage size of 500 gigabytes to about 10 terabytes. I think you can get 20 terabytes, but that's really on the high end. Typically, if you have one in your computer, it's going to be like a terabyte or two. Then we have solid state storage, SSDs. And these are called solid because they don't have any moving parts, in contrast with your typical magnetic disks. Now, these are newer. They're not very new now. They were really starting to become popular maybe 15 years ago, a bit later, 10 to 15 years ago. But when they were introduced, they were quite expensive. Now they're generally getting cheaper. But hard disk drives are still cheaper. But the advantage of these is because they have no moving parts, they are faster to access. Because with the spinning disk, you have like a head. With the magnetic storage, the hard disk drive, you have like a head on the thing and a spinning disk, and the disk has to come back to like the place. Has to find the place you want to get the files of. So that takes a while. With solid storage, this doesn't happen, and you can just like sort of access things much more quickly. And these range from like around 100 gigabytes on the low end. I think you'd struggle to get anything quite that small these days, but between 100 gigabytes and 2 terabytes on the large end. I'm sure you can get larger ones, but they'd be getting quite expensive. And then you have optical storage, which is like your CDs, DVDs, Blu-rays. And so these use like, so you have like the surface of a CD, DVD, or Blu-ray will have like some variation in the surface, like visually, which is either like pits and stuff on your sort of like non-rewritable ones. So like there'll be small like dips in the surface, or like there'll be variations in color if it's like a rewritable one. And what happens in this is like you have to, so the actual disk is portable, but you have to have like a specific like drive, like a reader in your computer or device to read them. And this has a laser in it that sort of reflects off the surface, that spins around, and then it sort of based on how much light it's reflecting, you can tell like if there's a dip in the disk or something like this, and that will store like the data. And these are slow, but they're portable, and they're sort of typically used for like films, music, things like this. Well, CDs are used for music, DVDs and Blu-rays more for films. But you can also get versions of them that can store data. And sort of their CDs are 700 megabytes, and DVDs can go, and Blu-rays even can go up to like 50, 100 gigabytes. DVDs are around like 7, 8, somewhere there. These have, apart from for films, these have really sort of fallen off in popularity because they're kind of slow. Even compared to like, you can get like solid state storage that's like, you know, your USB drives. And those are typically like both sort of easier to carry about, larger, and quicker. So, virtual memory. Virtual memory is, well, sometimes your RAM gets full with data and instructions, and so if you try to do something more with your computer, there'd be nowhere for it to go. And we came up with a solution to that, which was to take like part of your secondary storage, so like your hard drive, your SSD, and sort of allocate it to be used for like spillover for your RAM. So like when your RAM gets full, now instead of having nowhere to go, you start using that bit of your secondary storage as RAM. And obviously secondary storage is slower, so this will cause a slowdown in your computer's performance because you're now having to go to a slower storage medium. But slowing down is better than crashing, because if you didn't have anywhere to spill over, you would simply crash, or things would just go massively wrong. And slowing down is better than, that. Right, so images. How are images stored on a computer? Images are stored as 2D grids of pixels. And now a pixel is the smallest element of an image, and it stores like a single color, like a single point of color in that image. And obviously, if you like have just lots of different points of color, like imagine you're trying to like paint something with like just small dots of color. It's kind of like that. And so there are a few important like things that can inform like how that can affect how good an image is. One of them is resolution, which I haven't listed here. But resolution is just like the amount of pixels. So we typically store this by the image height and the image width. So it's like how big that grid of pixels is in terms of its height and color. And obviously with more pixels, you can like store more detail, like sort of about like I guess the general structure of things in the image. And there's also color depth, which is how many bits are used for each pixel. And sort of how many bits are used for each pixel affects like how many amount of colors you can represent, what range of colors each pixel can be. So for example, if you just have like 1 bit, you can only store black and white. If you have like 2 bits, you can now store 4 colors. You could go like black, white, yellow, and red, or something like that. Yeah. And images will also store what we call metadata, like at the start of the image file. And this is data about data. So metadata is data about data. So it'll tell you at the starter file, like what resolution the image is and what the color depth is. And this sort of helps, well, not only is it useful information that you might want to have, but also like it helps whatever program that's opening the image read it properly. And an image file size is the color depth times the image height times the image width. That's essentially the total number of pixels multiplied by the number of bits needed for each pixel. Right, so sound. How do you store sound on a computer? So sound is like a continuous wave. So like you can see here, this is like representing a sound wave. And in real life, like this is a continuous thing. You can see this going continuously over there, like that over time. But that'd be very hard to represent on a computer where we only can really like represent discrete things, like discrete bits. So what we do with a computer is we sort of sample sound, and what we mean by that is we sort of like sample where the wave is at a singular point. So here, like we can see that the wave is like down here currently, and the next one it's up here, and then it's down here, up here, and so on. And so we sample the position of the wave at like fixed points essentially. And then we can like reconstruct that wave based on those. So so then when we store it, we have this point, we have this point, we have this point, and then we can go like, oh, it must go like this between here, and this between here, and then this between here, and then this between here. And so that way we can reconstruct the original wave. And so there are 2 major things that affect the quality of, or how well a sound file represents the sound that it's intended to represent. And that is the sample rate. So that is the number of samples we're taking in seconds, and that is measured in hertz, which 1 hertz is 1 sample per second. And typically a typical sample rate for a computer file, a sound file, is 44,100 hertz. So that's sort of sampling 44,100 times per second, which is a lot. And that's how like we can get like fairly accurate sounds. And the bit depth, which is the number of bits per sample, which just allows us to more like accurately, the more bits there are, the more accurately we can represent the position of the sound wave at that moment. If it's lower bits, we can represent it less accurately. And so the file size of a sound file is an uncompressed sound file is the sample rate times the bit depth times the duration of the sound file. And so we move on to compression, which so the need for compression is because like files can get quite large, particularly video files. Sound and image also can get quite large, and we don't have unlimited storage. So we try to, a lot of the time, to sort of make these files smaller by compressing them, which is just like finding ways to represent them in less bytes, in less space. And so there are two types of compression, which is lossless, which is we don't throw the in lossless we don't throw any data away. We sort of just jiggle about how we're storing it, so we can store it in less, and the original file can be reconstructed fully if it is losslessly compressed. And for example, like a FLAC file is a popular like compressed lossless compression format for sound files for like music. And lossy compression is where we do throw away some of the data in order to make the file smaller. And obviously this can typically achieve like a smaller file than lossless compression, but it also means we cannot reconstruct the original file fully. Yeah, so this typically means that the result is of lower quality than a lossless compression or uncompressed. But the thing is, when we do loss compression, we typically try to sort of throw away the pieces of data you'll notice least. And for an example, an MP3 is a type of lossy compression, is a lossy compression format for sound files.